Check, check. Okay, good day, everyone. I am sorry I could not meet you physically this time, but rest assured that I am with you in this time of pandemic in the academic learning setup. It's just that we have so many things to attend to right now, so I decided to record my presentation today. All right, so in the previous weeks, or in the previous or previously, we were able to talk about permutation. And when we speak about permutation, we refer to an arrangement of objects where order is important, or a collection of objects as well where order is important. And this time, I would like you to think of this. Four swimmers vie for first and second places in a Swimathon 2021 competition. In how many ways can these be awarded, these two positions, considering that there are no ties for any position? So there are four swimmers and there are only two slots. So what can we do here is, by the way, feel free to pause and solve if you wish. And if you are ready, then just continue the video and check if you have the same answers. For the solution, so here are the two slots. We have the first and second places. And we will be using your slot method, which I introduced last time. So for the first slot, since there are four swimmers, so there are to award the place. Let's say A, B, C, D. But if one of them is ends, there are only three ways to award the second place. And by the fundamental counting principle, we simply have 4 times 3, and there are 12 ways in all to award these two places. All right? But don't worry, there's another way or another formula that could be used to solve this problem. And this is by making use of our linear permutation formula, that is, the number of permutations of n objects taken r at a time has this notation NPR. Some books use the notation P, then inside the parentheses we have NR, which is equal to n factorial all over n minus r quantity factorial, where your n, or your number of objects, has to be greater than or equal to the number which you are going to take out of your n. I think it's pretty logical because I believe it's logical because your n has to be greater than or equal to r. If your r is greater than n, then that's technically impossible. You will have zero ways. For example, how could you take, if you have 5 mangoes only, for example, how can you take 7 mangoes? That's why in this case, it's assumed, or we have to know, that the number of objects given should be greater than or equal to your R, the number of objects you take from the total. And note, however, that this formula applies only if there is no repetition of any element. So all elements are different and none of them are the same. Let's have the previous example. So the same given, the same problem, and we could see that our n is 4. How come n is 4? Because there are 4 swimmers. And how come our r is 2? This is the number of slots, the first and second places. And by making use of the formula we had, that's 4 permutation 2, I will just use this notation. It's equal to 4 factorial all over 4 minus 2 quantity factorial. This simplifies to 4 factorial all over 2 factorial. And based on what we did last time, 4 factorial could be expressed as 4 times 3 times 2 factorial. We stopped at 2 factorial because we know that we can divide it with the 1 in our denominator. And that leaves us 4 times 3, which is 12. So you see, using the slot method or using this permutation formula gave us the same answer. But note again that this formula is applicable if no repetition is allowed. Okay, moving on to, let's have this exercise. These are the three problems related to the first one. And since I'm doing a video or a recorded video of this, we will just expose them. But again, feel free to pause and stop and solve if you wish. Number one, in how many ways can 5 different books be arranged in a shelf if it has space only for 3 books? Note that all the books are different, so they are all distinct, and there's no repetition, of course. But there's only space for 3 books, which means there are only 3 slots. So for the solution, we see that n is 5 and that r is 3. So 5 permutation 3 will give us 5 factorial all over 5 minus 3 quantity factorial, which simplifies to 5 factorial. The denominator becomes 2 factorial. And continuing this, the 5 factorial could be expressed as 5 times 4 times 3 times 2 factorial, still all over 2 factorial. Canceling them or dividing them will become 1. That's why you arrive to 5 times 4 times 3, which is 60. Hence, there are 60 ways for you to, for 5 different books to be arranged in a shelf if there's only space for 3 books. And note, even if you use the slot method, there are 3 slots. The first slot is 5, second slot 4, third slot 3. You will still get 60. Okay? For the second one, how many 4-digit number or numbers can be made of the digits 1, 3, 4, 5, 7, 8, and 9 if repetition of digits is not allowed? It's good here in this given that all the digits given are non-zero, which makes it easier. Because if they're zero, then it's kind of more difficult or different. So you see how many digits are given. We have 1, 2, 3, 4, 5, 6, and 7. So since 7 digits are given, we see that n is 7. And since we are going to make 4-digit numbers only, then there's only slots for 4. That's why your r is 4. So by using the permutation formula again, we have 7 factorial all over 7 minus 4 factorial, quantity factorial. This simplifies to 7 factorial all over 3 factorial. And by definition again, we could express 7 factorial as 7 times 6 times 5 times 4 times 3 factorial. We stop at 3 factorial because again, we can divide it with our denominator. And what will be left is 7 times 6 times 5 times 4. And their product is 840. So there are 840 possible 4-digit numbers without repetition, making use only of the given digits. Eric, David, Mary, Becky, Jennifer, Trevor, and Christopher would like to occupy a row of 7 chairs. In how many ways can these chairs be occupied? And if you could notice, these people that I mentioned are actually the winners of MasterChef Canada. I'm a big fan of the show, actually. But again, I'm not advertising anything. It's just that I mentioned their names. Now, for the solution of this, it's clear that your n is 7 because there are all 7 people mentioned. And your r is 7 because there are also 7 chairs. So you see that n is equal to 7. That's okay. There's nothing wrong with it. It's okay. The only thing is that your r should not be greater than your n. By substitution, we have 7 factorial all over 7 minus 7 quantity factorial, which is 7 factorial all over 0 factorial. And I hope you could still remember that 0 factorial is equal to 1. And so by definition now, your 7 factorial is 7, 6, 5, 4, 3, 2, 1, and their product is 5040. So you see, guys, if your n is equal to your r, then the number of permutations of these distinct elements is just n factorial actually. It's actually a theorem. Okay. If there are questions, feel free to reach me. All right. Now, let's have another set of examples. My cell phone password consists of 3 digits from 0 to 9, followed by 4 letters from the English alphabet. How many passwords are possible if no digit nor letter is repeated? Now, take note, guys, that for your password, it's okay to start with 0 or not. It is actually okay because for password, you can make use of any digit. You can start with 0. However, that's why for some instances, however, like if you have 5-digit numbers, more often than not, you don't start with 0. But for passwords, it's okay to start with 0. The same thing with plate numbers. It's okay to have 0. No problem with that. So for the thing is, for the digits, that's 10 permutation 3. How come? Because there's 10 digits, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. There are 10 of them. And you are going to choose only 3. For the English alphabet, I hope you know how many letters there are. Our English alphabet has 26 letters from A, B, C, all the way until Z. There are 26 of them. But out of 26, you are going to choose only 4. That's why, oh, sorry. That's why for the number of letters, there are 26 permutation 4 or 26p4 ways. And for that, the total number of possibilities is the product of these two. Why multiply them? Because the fundamental counting principle is telling us that if one event can occur in this number of ways and the other event occurs in this number of ways, and given that these two events are independent events, then what you can do is the total number of combinations or possibilities is just their product. So we will solve this. We can actually use our calculators with this. But for now, we have 10 permutation. That's 10 factorial all over 10 minus 3 quantity factorial times. For the second one, that's 26 factorial all over 26 minus 4 quantity factorial. Simplifying this will yield this one. 10 factorial all over 7 factorial times 26 factorial all over 22 factorial. And using in their definitions, we have 10 times 9 times 8 times 7 factorial. So stop here to cancel this or to divide this. Times 26 times 25 times 24 times 23 times 22 factorial. Stop here because you could also divide it here. And upon division, you will be left with 10 times 9 times 8. And 26 times 26 times 25 times 24 times 23. And their product using a calculator is 258,336,000. Hence, there are these number of ways, these are the number of ways for you to have your password using the given. All right? Let's have the next one. Okay, actually, you should try this on your own. But anyway, I have 6 different English and 5 different math books. I have space for 5 books only, though, where the books can be placed vertically. In how many ways can I arrange 5 books such that 2 English books are on the left and the 3 math books are on the right? Meaning to say, out of the 6 different English, you're going to take only 2 of them. And 5 different math books, you are just going to take 3 of them and arrange them vertically 2 English at the left, 3 math books at the right. So all books of the same subject are together. They again, they are different English, they are different math books. So still, we can apply this concept that we had earlier. So that's out of English, 6, you pick 2. So that's 6 permutation 2 times. Out of the 5 different math books, you're going to pick 2 only. 3 rather. And that's 5 books in all that you picked to arrange. So this is 6 factorial all over 6 minus 2 factorial times 5 factorial all over 5 minus 3 factorial. This simplifies to 6 times 5 times 4 factorial all over 4 factorial. Cancel this. 5 times 4 times 3 times 2 factorial. Also, you could divide them, which will simplify to 6 times 5 times 5 times 4 times 3, or simply 1,800 different arrangements based on the given. Okay, moving on to the next one. Now, but before that, if you have questions again, feel free to reach me via Messenger. Now, how many distinct arrangements are there of the letters of the word Sasa? So we have the spelled S-A-S-S-A. So we are going to make 5-letter word strings out of these given letters, but we have to interchange some elements. And remember, the concept is if you interchange the same elements, then there's nothing new. It is not a new arrangement. Okay? Like this. If I interchange the S and the S, it's still Sasa. If I interchange A and A, it is still Sasa. However, if I interchange 2 different elements, S and A, then that produces a different arrangement. So the concept here is if you interchange same elements, then that does not produce a different or distinct arrangement. But if you interchange different, at least 2 different elements, then it is a new or it is a distinct arrangement, a new arrangement, something different. So let us list some of them. Let us list all of them rather. So of course, the given word Sasa is this one. It's one of the arrangements. And here's the second one, the third one, the fourth, the fifth, sixth, seven, eight, nine, and 10. And these are the 10 distinct arrangements or the 10 distinct permutations of the word Sasa. And let me remind you that this is actually very tedious, most especially if there are many elements. So you could see, you could actually verify that I have listed everything and there's no repetition, and there are only 10 of them. However, if there are so many elements that you need to arrange and there are some of them are repeating, then that is becoming very tedious. So we need to discuss a method wherein we could determine the number of ways without the need to list everything to determine it. And so let me acquaint you with indistinct permutation. When we say indistinct permutation, you are actually getting the number of distinct permutations, but the indistinct is telling us that of some objects or some elements have been repeated. May mga liwat-liwat repetition, and the number of permutations of n objects, not all distinct, that's why not all different, is n factorial all over r1, r sub 1 factorial, r sub 2 factorial, r sub 3 factorial, all the way until r sub I factorial. Where, if you take the sum of r sub 1, r sub 2, r sub 3 until r sub I, it should be equal to your n, or your total number of objects. But note again, this formula is usually used, or it applies, if you take all elements and there is no repetition. Sorry, and there is rather there is repetition of at least one element. So, like this. Going back here, we have SASA, S-A-S-S-A. You see that n is 5. How come n is 5? Because 1, 2, 3, 4, 5. There are 5 elements or 5 letters, of which 3 are S's and 2 are A's. You see that 3 plus 2 is equal to 5, right? And so by applying now the formula, that's 5 factorial all over. You take the factorial of the number of repetitions of each element. So 3. So that's why you have 3 factorial. Because the arrangement of these 3 S's will not matter. If the arrangement of the elements will not matter, you have to place it in your divisor or you divide it. And since also the arrangement of the 2 A's, if you interchange the 2 A's, also it will not matter. That's why I place here the 2 factorial in the denominator. So 5 factorial all over 3 factorial, 2 factorial. Simplifying this gives us 5 times 4 times 3 factorial. I stopped, of course, because of this 3 factorial here. Then this 2 factorial, it's the value of 2 factorial is 2. So I have here 2. I could divide the 3 factorial. So what will be left will be 5 times 4, which is 20, divided by 2, which is 10. And those 10, permutations were the ones I listed in the previous slide. So you see, either by listing or by using this indistinct permutation formula, we were able to arrive to the same answer. Next, how about how many 8-digit numbers are possible from the arrangement of the digits of 11,333,577? So your solution, we see that n is 8. How come 8? Because of course 1, 2, 3, 4, 5, 6, 7, 8. There are 8 digits, and of course all 8-digit numbers will be determined using these digits of this number. Now we see that there are 2 ones, or 1 was repeated, was counted twice. It was placed. It's present twice. No, there are 3 3s. There's 1 5, and there are 2 7. So you see that 2 plus 3 plus 1 plus 2 is 8. And by using by using the formula we have, that's 8 factorial all over 2 factorial, 3 factorial, 1 factorial, and 2 factorial. Okay? So simplifying this using your calculator for fast results, it's 1,680 8-digit numbers. So meaning, if you make use only of these digits, rearrange them, rearranging those digits that are different. I mean, if you take, for example, if you interchange 1 1, that's not allowed. But if you interchange 1 3 3 1 and so on, no problem. And if you do that, there are 1,680 ways in all. Next, how many? Okay, let's have the following problem. So let's just solve them. How many distinct permutations are there in the word Pilipinas? So how many letters? 1, 2, 3, 4, 5, 6, 7, 8, 9. So there are 9 letters. So our n is 9. There are 2 P's. There are 3 I's. There's 1 N. There's 1 A and 1 S. So you have 9 factorial all over, 2 factorial, 3 factorial. And you see I have here a couple of 1 factorials in the denominator. You see, no? But if you wish, if that's just 1 factorial, you may not include it in the solution because anyway, 1 factorial is equal to 1. And any number divided by or multiplied by 1 is still the number itself. So just using my calculator, it gave me 30,240 arrangements. Now, for the second one, I have 10 identical balloons except for color, of which 3 are red, 4 are green, and the rest are yellow. And I am planning to arrange them in a line. How many possibilities are there in all? Take note, we cannot apply the distinct permutation earlier because the balloons are identical except in color only. So if they are identical except in color, they are of the same size and they are different only in terms of color. So still, the indistinct permutation applies here. If 3 are red, 4 are green, 3 plus 4, that's 7. That means to say that there are 3 yellow balloons because 10 minus 7 is equal to 3. And I'm going to arrange them in a line. So we see that n is equal to 10 because there are 10 balloons. And there are 3 red, 4 green, and 3 yellow. So that's 10 factorial all over 3 factorial, 4 factorial, 3 factorial. And this simplifies to 4,200. Okay? Moving on to the next exercise. Remember, if you think it's too fast for you, you think you cannot catch up directly, feel free to pause and go back, okay? The third one. I have 7 identical math, 7 identical science, and 7 identical English books, and I am planning to put them in a single column. In how many ways can I do this? So we see that n is 21 because 7 plus 7 plus 7 is 21. There are 7 math, 7 science, and 7 English. So that's 21 factorial all over 7 factorial times 7 factorial times 7 factorial simplifies to 399,072,960. So imagine, if you have this number of identical math, science, and English books, there are 399,960 ways for you to arrange them. All right. Now, how about this? In how many ways can 3 people be seated around a circular table? This is a new topic related to permutation. So something circular. Let's say I have here A, B, C. This is one arrangement. And if you could notice, if I rotate this by 120 degrees, the A will go here, the B goes here, the C, rotate 120, A goes to B. That's why B goes to the position of C, and C goes to the position of A. It will result in this circle. If I rotate this circle once more, including the digits, by 120 degrees, the A goes to the position of B, B goes to C, and C goes to the position of A. It will result to this. And the thing is, are these arrangements different or are they the same? These arrangements are just the same. In fact, these 3 arrangements is just, if you think that these are 3 arrangements, no. This is just one arrangement in the circle. Because in this case, you could actually, it is just a result of rotation. And the order of elements with respect to the circle is constant. It's just that it was being rotated. The same thing, we have another this is another arrangement, ACB, and it's rotated 120 degrees clockwise. By the way, you can also do it counterclockwise. Hence, there are only 2 arrangements all in all of A, B, C if you place them evenly around a circle. And hence, let me introduce to you the circular permutation formula. That is, the number of permutations of n objects around the circle is n minus 1 quantity factorial. Again, this is true for circles. If it is on a line or a linear permutation, for example, that's n factorial only. But for circular, n minus 1 quantity factorial. Applying it, in how many ways can three people be seated around a circular table? This involves circular permutation because of this one circle with n equals 3. So by substitution, that's 3 minus 1 quantity factorial, which gives 2 factorial, or that's 2. And those two arrangements were the ones that I already mentioned in the previous slide. All right. Now, let's solve the following problems involving circular permutation. In how many ways can 8 children stand around a flagpole? So still, again, around a flagpole. So this involves circular permutation. So for the solution of this, our n is 8. So 8 minus 1 quantity factorial becomes 7 factorial. And that's 7 times 6 times 5 times 4 times 3 times 2 times 1, or 5,040. So there are 5,040 ways for them to stand around a flagpole. Next up, Anna, Nina, Xiaoyu, and Paul and Jack too would like to play Trip to Jerusalem by standing around a group of chairs. In how many ways can they stand? So if you know Trip to Jerusalem, it's like they are dancing around or they are walking while dancing around a group of chairs. And when the music stops, they have to sit. But anyway, there are 1, 2, 3, 4, 5 people. So this is a circular permutation that involves n equals 5. And so that's 5 minus 1 quantity factorial, or 4 factorial. And this simplifies to 24. And one more for today. It is given that n friends sit around a circular table. If there are 362,880 ways for them to sit, sorry, this is T, for them to sit, what is n? So this time we will do the reverse. We know that 9 factorial is 362,880. Take note that at some instances, last time I told you to memorize or to familiarize with the factorials until 10 factorial, so that it would be easier for you to deal in case you have to deal with this type of problems. So n minus 1 quantity factorial equals this number. And our goal is to solve for n. So that's n minus 1 factorial equals the value of this, which is 9 factorial. And you see there are both factorials. This implies that n minus 1 is equal to 9. So n minus 1 equals 9, and that's n equals 10. Hence, there are 10 people, or there are 10 friends that sit around a circular table. Questions? I will upload this PowerPoint presentation in our GC and also the video. God bless everyone and take care.